Hey guys, this is Garth. I wanted to give a quick video reviewing how to use some of products specifically for how to convert a binary truth table into a circuit in Logisim. This is kind of a precursor to the ALU assignment. We'll need this sum of products to be able to actually convert a truth table for an adder and actually convert that into circuitry in Logisim. We'll need this later on, so I just wanted to give this as a quick review. So, given a truth table, I've picked this one. This is tailor-made for our adder assignment. So I've got three inputs here: X, Y, and Z. And I've got two outputs: output 1 and output 2. So this truth table, take these inputs. So any combination of inputs. Say we've got, say we're looking at this row and we have X is 0, Y is 1, and Z is 1. When this combination of inputs occurs, output 1 does not fire and output 2 does not fire. So essentially we've got all possible combinations of X, Y, and Z inputs happening over here. It's binary, so we've got two possible options, 0 or 1. And we've got 3 inputs to deal with, so that's 2 to the power of 3, or 8 possible combinations. If you count the rows, we've actually got 8 rows here. So we've got all of our possible combinations of input data covered. And then in our columns to the right, we've got the cases of whether or not output 1 and output 2 fired for that combination of input. So for example, in this combination of input, when X, Y, and Z are all 0, output 1 fired in this case, but output 2 did not. So this is just basically how our truth table works, and we'll be making our own truth table later for a 1-bit adder circuit. So to convert this into a sum of products mathematical expression, we need to look at what cases cause output 1 to fire, and we'll look at output 2 later. We just want to look at output 1 now. So just this first column here. So we want to go ahead and mark when it does fire. So output 1 fires for this combination of inputs, and it fires for this combination of inputs. So we paid close attention to this, and we use it to write our mathematical expression here. So wherever we have a 0 for that input, we have to invert it. So looking at this first line, we've got X is 0, so that becomes X naught. So we bring down X naught in our sum of products expression. And then we look to our next input and we see that Y is 0, so we have to bring down Y naught. And then we look and we see that Z is also 0, so we bring down Z naught to our first product expression here. So this product, X naught times Y naught times Z naught, that covers our first case here where output 1 fires. And this literally is a sum of products in that this is a product, and then we've got 2 other products for the other 2 cases in which output 1 fires, and we've got all these products, and then we add them together. So we'll see how that converts into circuitry later on. But for this combination of inputs on this row now, we've got X is 0, so that becomes X naught, so we bring X naught down. And then we've got Y is 1, so we can just bring that down directly. So we've just got a Y here. And then we have Z is 0, so we bring down Z naught. And this is our second product here. Notice that we've added our first product to our second product here. And now we add on our third product, and we notice that X and Y are both 1, so we can bring X and Y down directly. And then Z is 0, so that has to be inverted, so that becomes Z naught. So this is our sum of products expression for output 1, and we say that this is in canonical form because this is as messy as this will possibly get. Now you can use Boolean algebra to simplify this if you'd like. So we could try to combine like terms. For example, if you had a really hairy expression and you noticed X and Y were shared in 2 terms, you might simplify that a little bit, and so that'll help you when you're making your circuitry later on. You'll maybe save a couple gates, and you'll definitely save a couple of input lines. So that's kind of outside the scope of the course, dealing with Boolean algebra. You'll deal with that later on in other computer architecture courses, but just something to keep in mind. These are not the simplest circuits that you could be making. So if you spot any cases where you can save on gates, not even through Boolean algebra, if you happen to notice that you've got an input line and it's for x times y times z, and then you use that later on in your circuit somewhere, go ahead and take that input line and use it in both places and save on that extra gate. You can do this by visual inspection, definitely. You don't even have to use Boolean algebra in all cases. So with this mathematical expression now, we can start constructing our circuitry. Now, there's two things we want to pay attention to. First, we want to pay attention to the order of operations. So in mathematics, whatever's in parentheses, that has to come first. So if we've got any operations there, we don't in this case, but if I were to give you an arbitrary expression and say the quantity x plus y in parentheses times z, well, you would want to add together x and y, and you would want to take the sum of that before you go ahead and multiply that with c, and that would be reflected in how you're constructing your gates. That would get passed through. If you were adding two quantities together, that would get passed through an OR gate. And since this is in parentheses, it needs to be passed through that OR gate first, and then the output of that OR gate would then go into an AND gate with whatever other expression that you were multiplying it with. So yeah, we want to pay attention to order of operations here. For sum of products, we only have to worry about addition and multiplication, so just remember multiplication comes first. So our products come first here. That was the first thing we had to remember. The second thing we have to remember is we've got our gates and what they equate to in terms of mathematics. So our AND gates are multiplication and our OR gates are addition. So when we're actually creating this as a circuit, look at our output and notice that we've got a product here, and x naught, y naught, and z naught all go into that product. So they all get fed into an AND gate because they're being multiplied together. That'll be a 3-input AND gate because we're dealing with the 3 inputs x naught, y naught, and z naught, and that'll have some sort of output. And then after we've got all of our products, we want to take each product and pipe that into an OR gate so that we add them all together. So that OR gate will have 3 inputs as well, because we want to add together this first product, this second product, and this third product. And then the final output of that OR gate will be our answer. That'll be for our output 1. So in Logisim, we want to go ahead and start making our inputs x, y, and z. So we draw our inputs, and then we extend our input lines out to the right a little bit. And so you can do this from left to right, or you can do it from up to down. Just try to keep them ordered nicely and spread apart. And then we want to add our NOT line. So we literally hook up a line here. This dot indicates that a connection has occurred. So we hook up a line and then we stick a NOT gate on it. So we've got our X NOT line at the top, we've got our X line at the top, and then we have our X NOT line at the bottom. And the same for our Y. We've got our Y line at the top and then our Y NOT line at the bottom. And you'll notice that the Y input is set to 0, and then when it passes through the NOT gate, this line here is highlighted green to indicate that it has become a 1. This darker green, that's a 0, and this lighter green is a 1. So after passing through this NOT gate, the 0 has been inverted into a 1. So now this NOT line is active. It's live now. So that's just a good hint of, yes, these lines are all hooked up correctly to the NOT gates. Once you start playing around with the gates, you'll get a feel for what to expect. So that can kind of help you to notice when you've been successfully making these connections. Sometimes it appears that you've made a connection, but it is not so, and you'll have some errors in your circuitry. So just be sure to pay attention to that. So now that we've got our line set up, we can go ahead and look at our sum of products canonical form expression, and we look at our first product here, and we pipe the input lines into our AND gate. So we have x naught times y naught times z naught, and we want to pipe these lines into our AND gate. So we take our line for x naught, we look at our x input, and this is the x line, and this is the x naught line, and we want to take that line and we want to bring it down into our AND gate. And then we want to do the same for our Since we want y naught here, we want to look at our y input. Here's our y naught input line, and we want to bring that down into our AND gate. And then we also notice we want z naught. So here's our z input, our z naught input line, and we bring that down into our AND gate. And so the result of this AND gate, the input coming out the bottom here, that will be the answer for the product for this first term in our sum of products expression. So it's also a good idea. We want you guys to try to label your inputs here. Logisim has a very nice feature built in so you can label your inputs. You can label your gates as well. We definitely recommend labeling your gates, especially on a test. It's very good for going back over your work when you've got a bunch of gates connected up. Sometimes you can have errors, and if you don't have your gates labeled, it's very, very difficult to go back and trace your errors if you don't know what each gate is supposed to be hooked up to. So I definitely recommend labeling those. So we've got our second AND gate. So this represents this second product here. So I've got x naught times y times z naught. So bringing our x naught line, extending it a little further now, we're able to take this line and pipe that into our AND gate. So we have our x naught line coming in, and then next we want our y line. So we just take our normal y line, not our y naught line, just the y line. So we have this coming into our AND gate, and finally our z naught line, which is down here. So we've just got a connection here going on, and that gets brought over and brought into this AND gate. And so notice that we've got these connections being made. So this line is shared. This one x naught line, we see that it's shared between the two AND gates. This is perfectly alright. This isn't going to affect anything. Some people might think, well, if it's going into both AND gates, doesn't that change what's on this line? Well, no, it doesn't. The gates are a feed forward sort of function. So we've got the X input line, and then it travels down and it goes through the NOT gate. Then it kind of splits out, and then it goes into each of the AND gates individually. And it doesn't matter what happens inside the AND gate. It doesn't care. It's not going to feed back onto the line. It's just a feed forward. So feed forward meaning it's going to, whatever is on these input lines is going to affect the output product for the AND gate. It doesn't affect anything on the input lines. The input lines are not changed at all. So it's perfectly alright. It's perfectly alright that we've got these connections going on here. And so we've got our third AND gate here, and so this is for our last product. We have x times y times z naught going into our last gate here. So we have our x input line, and we just extend that over and we bring that down into our gate. And then we notice we need y, so we've got our y input line, and we bring that over and we pull that down into our gate. And then we've also got our z naught input. So we've got our z input here and our z naught line. We want to extend that over and bring that into our gate. So in these slides, I want you to notice that I've actually missed a connection here. There's a little blue dot, if you can see it. It's very small. But I've actually missed a connection for the z naught line for this last gate. Notice how this line is a little bit off when you compare it to these other gates. I don't see any difference here, and I won't notice a difference until I actually look at the final answer and I try turning on some of these combinations of inputs and actually observing the output to see if it matches what's in the truth table. So again, it's very important to be labeling your gates, because I'll go back and I'll say, oh yes, this line that I haven't made a connection to, oh, that's definitely the z naught line that needs to be here, so I can go and adjust that connection. Just take especially good care. So now we've got our three products here. We've got the first product by this line, and the second product represented by the output of this AND gate, and our third product for this gate. And we want to add them all together. And so we've got three products here, so we've got three inputs. And since we want to add them, we will need an OR gate. So this OR gate represents addition going on. So I'm labeling the expression that this OR gate represents. So we've got our individual products here, and then they're all being added together. And the output of this OR gate is our output 1. So this should now match, well, it won't because I've missed this input line, but this should now match the truth table. If we were to test any number of x, y, and z, any number of combinations of inputs here, the output should match. And so now we're not done though. We've got our truth table. We had output 1 and we also had output 2, and output 2 had two occurrences which it fired. It fired in the case where x was 0, y was 0, and z was 1, output 2 fired. And then we've got another instance where output 2 fired as well when x was 1, y was 0, and z was 0. So we want to pay attention to these inputs, and we want to bring this and write. We want to bring these down and write a sum of products expression for this. So we look at the first input. We see that x is 0, so we invert it, so it becomes x naught times. We look at y. We see that that's 0, so y naught times. We look at z. That's just 1, so it's all right to bring z down directly. So we bring down z. So we have x naught times y naught times z. That's our first product. And then we look at the second case in which output 2 fired, and we see the inputs for that. X is 1, so we can bring that down directly. And then we look at y. Y is 0, so we're going to have to invert that, and we'll bring down y naught. And then z, the same thing, that's 0 as well, so we'll have to bring down z naught. So we've got x times y naught times z naught for our second product. And we've only got two products here in this sum of product expression. It's a little shorter than our first one. Since we've only got two cases here where output 2 fired, and before we had three cases and output 1 where it fired, so that was why we had three products before, but in this case we've only got two. So this will be a little bit different. You'll notice that the AND gates won't change. We've still got three inputs coming into each of our AND gates, but in our final OR gate for output 2, notice that we've only got two products here, so we only need a 2-input OR gate. We don't need a 3-input OR gate like before, so we have some minor differences going on here. So we take our sum of products canonical form expression here, and we look at our first product term. We've got x naught times y naught times z, and we go ahead and we set up an AND gate, and we bring down our x naught line. So we've got this x naught line coming down into our AND gate, and then we've got our y naught line. Here's our y input, and here's our y naught input line, and that gets brought down into our AND gate. And then finally, we know we want z to go in our AND gate as well. So we got our z input, and here's our z input line, just our plain vanilla z input line, and that gets brought down into our AND gate. And so that's our first product. And then we look at our second product for output 2, and we see we want x times y naught times z naught. So we'll need to bring down x. Here's our x input line. We extend that all the way over and bring that down into our AND gate. And then we've got y naught. So here's our y input line. Here's our y naught input line highlighted in light green here, and we want to extend that over and bring that down into our AND gate. And then we finally want to bring down z naught. So here's our z input and our z naught line, and we want to extend that over and bring that down. So we've got our two products here, and this is separate. We've built this onto our existing circuit. So you can go ahead and continuous for any number of outputs. You can do 2 outputs, you can do 3 or 4. You'll be using the same inputs no matter how many you have, and you'll just be adding more AND gates that eventually get piped to an OR gate and present an output to you. So these AND gates are logically separate from this first set of AND gates. So you could actually delete the circuitry for output 1. You could just have the circuitry going on here for output 2, and it wouldn't be any different here. These are like logically isolated. So if I had this all in a separate circuit for output 1 and all in another separate circuit for output 2, it would be the same as if they're combined together in this circuit, how I have them here. The final output would be the same. This is just to explain that we can share these x and y and z input lines wherever we like, and it won't change the answer for either output 1 or output 2. And because the logic gates here are a feed forward sort of function, and that whatever's coming into the gate doesn't change the existing input lines, it only changes the output. So now that we've got our two products here, we can go ahead and add our OR gate so that we sum both of the products together, hence the name sum of products. So we add this product to this product. So we bring these two lines into this OR gate. And then we bring an output, and we label that output 2. So now you can begin turning x and y and z on and off, and you'll notice the lines will individually highlight, and the outputs of all the AND gates will highlight, and you'll get a different response for output 1 and output 2, depending on whatever the truth table indicated when output 1 or output 2 fired. So this is a circuit. This is how you use sum of products to turn a binary truth table into an actual circuit in Logisim, and I hope this video is helpful. We'll be using this later on. I'll give you a truth table for a 1-bit adder, and we'll use this as part of a ALU later on, and we'll derive the 1-bit adder expression. We'll derive the truth table, and then we'll proceed to convert the truth table into an actual circuit, and then we'll use that circuit in an ALU. And so we'll kind of represent a portion of the CPU that performs all of the arithmetic operations, and we'll create that completely from scratch later on. So that's all for this tutorial. Let me know if you have any questions.